Thank you, everybody, for joining this presentation of 5G-INDUCE. It's an ICT 41 project which comes towards its end. And we would like, with this presentation, essentially to show what has been achieved in terms of the use cases, with the main focus was, of course, the industrial vertical sector, and also give some highlights of the project. So I pass the floor to our coordinator, Professor Franco Davoli from CNIT, in order to give an introduction to the 5G-INDUCE first. Franco, please.
Okay, thank you, Dimitris, and welcome everyone to this workshop. I'm Franco Davoli from the University of Genoa and CNIT, the National Consortium, Inter-University Consortium for Telecommunications in Italy, and I'm coordinating on behalf of CNIT the 5G-INDUCE project. Dimitris, who was talking before, is the technical coordinator, and he will go into more detail afterwards. So in 5G-INDUCE stands for Open Cooperative 5G Experimentation Platforms for the Industrial Sector NetApps. And it's a project from called ICT 41 that started in 21st January of 2021. Originally has to be concluded on December 23, but then we requested for an extension that was granted, so we concluded in June 24. The budget of the project, as you can see, is 6 million euros with 8 million euros total cost, and we have over an effort of over 1,000 person months. The main goal of the main concept of 5G-INDUCE has been to provide an end-to-end orchestration platform to enable experimentation infrastructures for advanced 5G network applications in the Industry 4.0 sector, and to validate the 5G readiness of telecom operators and application providers through experimentation on a 5G system platform. So next slide, please. The main concept underlying 5G-INDUCE stems from the fact that the cloud paradigms of IaaS, PaaS, and SaaS, software as a service, define the type and boundaries of offered service per actors, and in particular, actors that offer IaaS services, infrastructure as a service, provide their computing and networking infrastructure to third-party platform or software providers, that are usually referred to as tenants through virtual infrastructure manager. Then, given the complexity of management and control operations that are performed by VIMs, a large part of them often is delegated and automated by service orchestrators. And programmable resources are an integral part of the softwareized infrastructure in 5G, and data centers and edge computing resources that serve communication needs of the microservices that compose applications are owned by telecom infrastructure and service providers. So next slide, please. So in this scenario, a great relevance has been given already in our previous project Matilda, and then enhanced in 5G-INDUCE, to the separation of orchestration concerns between the world of applications, so application developers that are used to work in a cloud-native platform, and the network functions virtualization platforms. These, in fact, stem from a similar paradigm, but are oriented to providing network services to the vertical applications so that they can see a flexible dynamic resource allocation, and that this resource allocation platform can be tailored to the needs, to the communication needs of the applications. And at the same time, they should allow the network service providers and infrastructure providers to compete in the telco marketplace in order to offer the best possible services to the application providers, to the verticals. So this is the main concept that was behind the separation of orchestration that we have used in 5G-INDUCE. Next slide, please. And 5G-INDUCE basically has three main areas of intervention. One has been the NetApp management, the development of a NetApp management platform in a full stack composed of a network application orchestrator and an extended operation and support system which sits on top of the network functions orchestrator, virtual network functions orchestrator for the service providers, for the network service providers. The second area of intervention has been the development of advanced network applications to demonstrate a number of services, of applications, of verticals that will be illustrated later on. And the third area of intervention has been the setup of three experimentation infrastructure platforms, one in Greece, one in Italy, and one in Spain, which will be also illustrated in more detail in the following. Next slide, please. So this is just a view of these development areas that I mentioned, but we don't lose some time, too much time on this, because this will be described in more detail in the next presentations as regards the platform and the applications and experimentation facilities. This is a more detailed view, but also in this case, Dimitris will go into some more details of the structure of the network application orchestrator that whose goal is to provide network application developers with an environment that is close to their cloud native environment to which they are used to work with, and in order to define and modify the application requirements. In the OSS, which is in turn the operation support system that has the task of creating the slices required to comply with the needs, with communication and QoS needs of the vertical applications on behalf of what requested by the NOW. The platform is integrated, as we said, over three experimentation facilities in Spain, Greece, and Italy. And on these, we have experimented and verified and tested the vertical applications. This, again, is a more detailed view of the experimentation facilities, which are at Ford, Valencia, and Ericsson Photonic in Spain, at PPC premises, and with 5G connectivity provided by OTE in Greece, and in Beko Europe, formerly Whirlpool, in Italy, in Cassinetta, with 5G connectivity provided by Wind3 and by, in another form, by CNIT with its DevOps testbed. So with this, I think we can go to the next. This has served more or less as an introduction and an agenda of what will come next. So Dimitris, please, the floor is yours again.
You are in mute, Dimitris.
Okay, sorry for that. Okay, so as Franco said, we will go through the main part of our platform. Okay, so the next presentation is on this 5G-INDUCE now and OSS platform, which is the core, of course, of the whole functionality for doing the onboarding deployment over the infrastructure. And as a next step, then, of course, we'll go and check all the actual use cases that have been developed and tested in the different facilities. Okay, so the key purpose when we start building even this platform from the beginning was to provide an end-user-friendly environment in order to do the onboarding, the deployment of applications, so have a more application-oriented or end-user-oriented approach. And users should define also application parameters, and that is by extending actually the platform towards SLA management, parameters related to SLA, but also parameters that are related with a network, and that is policies. The core part of the platform is, of course, the capability to deal with complex network applications, meaning applications that are built in the form of chained microservices over Kubernetes platform. And that defines also, according to us, what network application is, or an NApp. Okay, so you will see this term many times, the NApp, in our presentation. So a network application, it's a full application. It's an end-to-end application that has also the networking constraints according to the infrastructure where this needs to be deployed. For that reason, each application is split into application functions and network functions, that all of them are joined, of course, together as linked microservices, composing graphs, which then, according to the requirements that the end user said, these are requested from the infrastructure. Then the infrastructure, the OSS, again, that is the final part, should have the capability to dynamically configure. And this to configure the resources. And this dynamicity comes in two steps again. It's on the OSS part that has to do with the resources, but to the programmable resources, but it is also related with the deployed application. So the capability of the end user essentially to manage the already deployed applications. In other words, it's the runtime process where we wanted also to have this dynamicity. This is the picture that also Franco showed before. So our focus will be on this part, this essential part. It's the core part of the platform. And this platform, as it was mentioned before, consists of primarily 3 layers in our implementation. Okay, so the first layer, the upper layer, has to do with the network application orchestrator, the part where we have the NApp registration, the onboarding. It's where we request the end user request of the operational parameters, the policies, and like essential thing here is also the automated translation of this NApp into NApp microservices into deployment requests for the OSS in a language that it can understand in terms of how this should be then deployed, okay, and used by the OSS. Then comes this layer in the middle, okay, the operating support system. It's essentially the part of a resource orchestrator, and this is the part where now we have the selection and the selection of proper resources at the edge facilities where the application needs to be deployed. We need also the update, create, delete of network services. And as I mentioned before, the essential part is also the dynamic reconfiguration of the network slices according to the policies or what to the requests that are coming from the end user. Finally, it is a layer here in the middle. Basically, it is referred in our development as the southbound interface of the OSS. And this southbound NAV convergence layer, as the name says, it attempts to provide actually a convergence between the OSS and any different type of infrastructure that we can address, simply because we see at the moment that, okay, it's perfectly fine to address more advanced programmable infrastructures. Okay, that was the core purpose actually of the whole development. But we see that at the same time, there are infrastructures that are legacy infrastructures that provide more static type of configuration, or according to some standards like HMAN, for example. So we wanted to have this compatibility, and this is one of the essential parts of compatibility with diverse set of infrastructures, and of course, then in turn support both public type of infrastructure deployments coming, for example, from operators, okay, who want to provide this as service to the infrastructures, or have advanced private infrastructure deployments, so private infrastructures that can manage their own resources. And in our case, we try to cover all of these different options. This is a detailed sketch of our architecture. Okay, don't be afraid, I'm not going to each individual, okay, technology and that has been developed and how this interface. There is a lot of background work. Just want to give a very brief overview actually of the whole control cycles that are implemented. Of course, on top we have the end users coming with a request. The request have to do with the NetApp component registration, constraints that can insert it, and policies. So these are composed together to form, first of all, to store this information. So we have our repository here. Repository, of course, later can be extended to any kind of even going towards marketplace, for example, with through this interface. But the important one where the focus was is, of course, to have a persistency built and the composer from all the different requests, which are then essentially translated to slice requests, translated to a request which is understandable as a next step from the OSS northbound in order to proceed with the appropriate deployments according to what the end user requests the node. Okay, there is an advanced slice negotiation also part here. Okay, for the case, of course, that these resources cannot be met, and we need to reconfigure some things. Okay, so entering now the resource orchestrator, the OSS part, there are the three options that I mentioned before. We may have no programmability, black box resources, or simply a selection of available slices that are underneath. We have seen that in some cases, and it is something that was easily, of course, to be supported. Second thing is, of course, we have some partial programmability through NVSol 006, for example, compliant resources where we can have programmability at the level of the computational resources, and then it's the full programmability. It's the most interesting part also for our development, where we have the full mechanism, full stack here in order to provide, to do the deployment over programmable infrastructures, but also manage at the second stage also these programmable infrastructures. This is more towards the advanced 5G or even 6G later on. The outcome from this one is the generation, of course, of the appropriate slice. So materialize the slice and manage the Kubernetes platform, which is on top of that. By doing so, then we are at the position now to start doing the deployment of the application, so of the microservices, okay, and the application then. So at that stage, there is a connection back to the network application orchestrator, where the whole process is instantiated, and now we are talking about a running network application. This is the whole deployment cycle, and of course there is the runtime cycle. So during runtime, when application is running, then through analytics and profiling aging, monitoring information, and relying on the policy execution engine, okay, then here at that level, we can see if there are reconfiguration requests that are triggered. These are managed then by the NetApp Lifecycle Manager, okay, which of course in combination with the deployment manager, then the enters and repeats, okay, the previous loop in terms of configuration of resources. This is a very high level view actually of the whole architecture. Next, I will go a bit quickly also through the 5G-INDUCE platform environment. So for this one, I think it's better. I have some slides, okay, to see, but I will jump directly to the actual interface that we have. So this is the interface we have developed. On the left-hand side, you will see essentially, I would like to focus more on these three: the components, the application, and the instances. The first step starts with the components, where the components, we have all the different microservices. So this is a list of the microservices. At some point, you see that many of them, so for example, some of them for use case 8, okay, and the management, then for use case 7, use case 6. So you'll see many of these application components, as we call them, or microservices, which compose, okay, the applications that we want to run. There is a certain environment where we can create a new application. Creating a new one, we give a name, we select architecture and different many parameters that I will not go now in detail. Okay, like for example, okay, here is the execution parameter, how much RAM, storage, CPU, environmental variables, or exposed interface that this should have, etc., etc. Okay. So as we build and we save this, then the next step is, of course, to create the NetApps, the application, as we say here. So we can create from here a new one by joining different applications. Here you see a list of already existing applications, and we can also recall some of them. So for example, the use case 5 application that we can see here, okay, then we can go and create, okay, pick this up and create an instance. By creating an instance, okay, so that means initiating. So what one has to do is essentially pick up a certain instance name, like for example, use case 5 test at this point. Okay, and then the next part is to reconfigure each one of these components from the networking perspective now. Like for example, select where this needs to be run, okay, the type of it, and in which node, for example, this has to be executed, okay, and many different parameters, but also edit already existing environmental variables, for example, that are here. Next step is, of course, the type of it. Okay, so the slice type for each one, where this should be deployed, name BD, MIOT or URLC, okay, and give also several parameters, like for example, what will be the requested maximum rate, minimum guaranteed bandwidth, etc., etc. Okay, so you see that we have the network application in a more generic form, but now once we do the deployment, we pass the specific variables in each one of them. So I will again come back, okay, essentially in order to proceed, then we proceed and we start the instantiation. Once we have an instantiation, then basically we move to the instances. So instance may be pending for deployment or waiting some configuration, or maybe already deployed over a certain platform. So this, if I pick up this one, it's for use case 7. So one can see again, for example, the graph here. At the moment, we are going through an update in our monitoring system. So if that wasn't the case, so that is for another project. So basically, we see for each of these components also the CPU, the RAM usage, disk usage. We can select also different parameters. So here we have a final step if we want to reconfigure something, of course, okay, or monitor simply the different instances that are running. Okay, similar here, there is a dashboard. At the moment, due to the updates we are doing, we don't see something, but okay, by selecting through the Grafana what should be demonstrated, then we can also have different entities here being demonstrated. Okay, so this is like a quick overview of the platform we have used. Okay, and with this I conclude my presentation, and perhaps moving also to the more interesting part of what will be the results, what are the use cases, the infrastructures where we have run all our interesting use cases. So I will stop my presentation here at this stage, and will pass the floor to Diego from Ericsson in order to proceed with the Spanish experimentation facility and the use case that ran there.
Hi, Dimitris. Thank you.
So,
Yeah. Good afternoon, all. My name is Diego San Cristobal. I'm with Ericsson Spain, and I've been involved in the solution design and deployment of the infrastructure of the Spanish experimentation facility in 5G-INDUCE. In this EXFA, Ericsson is the provider of 5G network equipment. Ericsson's interest in this project is to show the benefits that 5G and Industry 4.0 can provide to each other. We consider 5G a key enabler for the communication needs of Industry 4.0, while Industry 4.0 can boost the demand for 5G deployments. The network architecture key concepts that are applied in this project are: first, the 5G's performance and flexibility. And this makes 5G a better fit than any other communication alternative. It delivers better performance than any wireless alternative when devices with mobility are required, and it can be deployed and modified faster and more cost effectively than cabled alternatives. Also, we have deployed a non-public network solution where we are using a shared centralized 5G core located at Fivetonic Lab. And we have deployed a private radio access network and private user plane function at the industrial vertical premises. The benefit for the industrial vertical is that they do not have to deploy a full private 5G network, only a part of it, resulting in faster and easier deployment and maintenance. Another interesting concept is the slicing. With slicing, certain application traffic can be isolated from the rest of the traffic, and an agreed quality of service can be guaranteed for that specific application traffic. Finally, we need a network architecture that allows edge computing. This is why we are deploying an UPF together with the RAN. The 5G network makes the local breakout of user plane traffic, and then it is up to the industrial vertical to have their applications running on premises or on an edge app platform or in the cloud, depending on their latency expectation. And Ford is the industrial partner in EXFA Spain. The use cases are useful for Ford, and they are tested at Ford's premises. And this is the perfect environment to experiment the ideas mentioned before. For more details on 5G and Industry 4.0, you can refer to a white paper to which many partners in 5G-INDUCE have contributed to. It is published on 5G PPP webpage, and it's titled Innovation Trends in Industry 4.0 Enabled by 5G and Beyond Networks. There is also a podcast on Industry 4.0 and 5G intertwining topics that is published in the 5G-INDUCE YouTube channel that you can check out. Regarding the high-level interconnectivity in between all the sites that we have in the Spanish ESFA, I'm going to start with this corner here on the bottom left. This is the Ford premises in Valencia, where the RAN coverage, the 5G coverage needs to be deployed. And we deploy here the RAN. We also deploy the UPF to get the local breakout of the user plane traffic, and a server for applications where the applications can be run when running on premises computing. Then there is a fiber connecting to the University of Valencia. The University of Valencia is around 20 kilometers from Ford. So here we have an edge platform where we can also run applications, and this makes the edge computing side of this solution. Then we also need to reach 5-tonic. So we did this by connecting through Red Iris, which is a backbone network among research and academic institutions in Spain. So we can reach the 5G core. And we need to reach the 5G core because the 5G core is the one that controls that the devices are allowed to connect to this network, and also controls the establishment of the data sessions for those devices. We also connected 5-tonic to the CNIT site to get access to the 5G-INDUCE now and OSS, and to get the possibility to use the features provided by this, like onboarding the applications either on the edge platform or on premises. Okay, the testing area is based in Ford premises, and we have 3 use cases that include AGVs that are going to move around the premises. And we need to provide coverage to this outdoor area depicted here, and to 2 warehouses where indoor coverage is needed. Okay, this is the picture of the same area, but the view is from the opposite side. The yellow line is the track that the AGV is following, and we decided the number of Ericsson's dots that we needed to install to provide the indoor coverage, and then 1 radio in the outdoor to provide coverage to the outdoor area. This is the 5G RAN solution. I'm starting below here with this router. This router is placed in the rack, and it provides connectivity among all the other components inside the rack, and also to the outside world, including the 5G standalone core that we need to reach. For the indoor coverage, there is a baseband and an indoor radio unit, and then the Ericsson dots are connected to this last equipment. And for the radio in the outdoor, there's a baseband and it's connected to the radio. We also need a GPS signal. We have a receiver for this GPS signal because this is the way that we get a clock reference that is received by the router, and then the router distributes this signal through PTP for the synchronization of the radio signals. And these are the pictures of how it looks installed there at Ford premises. This is the rack where all this equipment is, except the antennas. The antennas, the Ericsson dots are in the warehouse ceiling, and then the outdoor antenna is in a pole outside the building. Okay, we have 3 use cases. The first one is the autonomous indoor fleet management. Second one is the smart operation based on human gesture recognition. And the third one is VR immersion and AGV control. And now my colleagues are going to explain these use cases more in detail. So we are going to start with use case 1. For this, I will hand it over to Enrique Sierra from University of Burgos. Please, Enrique.
Thank you, Diego. I'm Enrique Sierra from the University of Burgos. We have developed this first use case with ABB, and this use case is an app to orchestrate the indoor and outdoor AGVs to execute an industrial use case. Here we can see an outdoor AGV and indoor AGV. The outdoor AGV and the indoor AGV are sending the sensors and other information, other internal variables to the edge. And in the edge, we have AGV coordinator is receiving all that information and is orchestrating the movements of the AGVs to complete the logistic process. And there is one specific module in the edge also that is called the logistic process manager that is used to define the state machine to run the logistic process, or the production process can be configured to run whatever kind of logistic process or production process. Next slide, please. Here we can see the outdoor AGV in the left picture, and we can see how the indoor AGV and the outdoor AGV are synchronized and moving one pallet. The outdoor AGV is moving one trolley, and the indoor AGV is pulling the pallet on the trolley. Next slide, please. Here we can see some of the main KPIs. We can highlight for example, the perceived operation latency is one of the most important KPIs in this use case, and also it's important the time to deploy the service. Next slide, please. To conclude the remarks of this use case, we have seen that the use case has been correctly executed. We have seen that the latency perceived by the user is very low, and it's something that is very, very good. It's possible to coordinate different type of AGVs to execute indoor and outdoor applications. And also it's important to say that it's possible to combine this use case with other applications like remote control solutions, like we'll see in the next use cases. And also it's important to say that it's possible to deploy the fleet manager as a service. And to highlight some future applications, this use case will be run in automotive sector, logistic applications, and also in whatever kind of production. This is all for the use case 1.
Okay, thank you, Enrique. Now we are moving to Manuel Fuentes from 5Com to explain use case 2. Please, Manuel.
Hello, can you hear me?
Hello, yes.
Okay, yes, so the second use case of the 5G-INDUCE project is about the smart operation based on human gesture recognition. So in this use case, what we wanted to demonstrate is how the workers in an industrial environment can, by using some gestures, can provide orders to AGVs that are in that particular environment, such as stopping, moving the vehicle forward, or even backwards. This is the setup that you see here. Is the setup we use for the use case. So on premises at Ford, we have the AGV provided by ABB, and then it was equipped with a 3D camera for taking the gestures, and also with a tablet in this case. And then the information from the gestures that we were taking was, or the video, better said, was sent through a 5G modem to the radio parts, to the network, and then at the edge, either at UPV premises, as Diego was explaining, or at Ford, we were able to execute the network application that was based on 3 main containers. The first one was for video encoding and decoding. The second one was for the gesture recognition itself. And then the third one was for moving the AGV. So what this network application did was to, from this video feed, analyze it, get the gestures, and then produce 2 different streams. The first one was going to the tablet that was installed in the AGV. So the workers were able to see the video, but processed with the gestures. And at the same time, this particular gesture was providing a second stream that was the different orders that were given to the AGV to move. If you go to the next slide, we can see how this works. But more in particular, I want to put emphasis on the 3 phases we executed. First, we did some pre-testing on 5Tonic in Madrid, but then once everything was set, we decided to go to Ford. And the first phase that we did in January last year was by using a manual onboarding of the components on the network, we tested the functionalities. Then in a second phase, we tested the same functionalities, but combined with the use cases 1 and 3, which are the use case that we just saw about how these 2 AGVs can coordinate themselves, and also a third one, which will be explained later, about using virtual reality and 360 video. And then in the third phase, we validated all use cases together, but also by doing the onboarding and the deployment by the platform of 5G-INDUCE. So we were using this platform to deploy the containers, and then we were executing the demo in a different place than we did in the second and first phases. If you go to the next slide, here we just highlight the most relevant KPIs. As I was explaining, first in 5Tonic, we do some pre-testing, and then we saw there that the end-to-end latency, the video quality, and the throughput that we needed, and also that the service deployment time was okay. And then we went to Ford and we tested similar KPIs, and we observed an glass-to-glass latency of 224 milliseconds on average, and also that the video bitrate was as needed, because we were using the platform by providing the different requirements. And then if you go to the next slide, we can see some measurements and also some conclusions. So as you can see here, this is a graph of the glass-to-glass latency we got, the video end-to-end latency. We did 120 snapshots as reproduced in the image on the right side. We got the time from when we sent it until we got it in the tablet that you see here. And then we just did the average. We got this value that for the video in particular, when doing this particular setup, we even got lower values for end-to-end latency. But yeah, so we think that this, we saw in general that the impact of 5G was almost negligible when comparing with also the application itself, which is good. And also that we saw that the use of the platform was very beneficial for us to understand how to deploy services, and also how to do it in order to have, when we are having high data rates and especially low latency, which we saw that was reduced. And then some benefits about the use case. We just proved that the human gestures could be a good practice for avoiding accidents, because you can do this kind of gestures before the AGV approaches the worker. And then also that the combination with 5G was a promising solution. And we ended up having a very nice use case demonstration, as you saw. And that's it from our side.
Thank you, Manuel. So now we're handing it over to Miguel Ángel Martínez from Nirvabuena VR. Please, Miguel Ángel.
Hello.
Miguel Ángel. Yeah.
Well, the use case number 3 has been focused mainly in the monitoring of an automated guided vehicle, AGV, using the 5G network. For this, we installed a camera, 360-degree camera, feeding a 4K video to the network, and connected with the 5Com modem. And also the AGV and the modem was sending status information, real-time status information to the edge. In the 5G edge is the network application itself that is taking the video feed and also the data from the AGV and the 5Com modem, and then combining the different data, it constructs, build a graphical overlay that is shown over the video, like you can see in the left, in the right, in the upper part of the slide. Then from the edge, using the 5G downlink, the video resultant of this combination is sent to different devices, could be a VR headset or a mobile smartphone. And then the operator can have a quick view what is happening around the AGV, and also to check the real-time status information from the devices. Okay, next slide. Well, the conclusions of all this work has been that the main challenge that we were at the beginning of the project is if the uplink in 5G was able to transport a 4K immersive video, and finally we have checked that the capacity, the uplink capacity has not been a constraint in this use case. That is a good news. On the other hand, we have get a second conclusion, is that we need to study more deeply the impact of jitter and packet losses in the radio links, because we have checked that this part is in affecting to the video quality. But with the network that we have in this use case and in this XFA, we can carry out the use case perfectly. Okay, and the third slide is about the benefits of this use case. That is that we have been checking that we don't need to have personnel in unsafe or remote locations. With this use case, you can avoid risks, and also it's a help to monitor remote or complex spaces in different facilities. This is especially useful for manufacturers, industrial factories, huge installations, and mainly for unsafe spaces for humans, such as on an oil refinery, heavy machinery mines, or chemical industries. This is a good way to have a clear look at what's happening in the place without have human presence in this place. And that's all for the use case number 3.
Okay, thank you, Miguel Ángel. Now, please, Dimitris, could you play the video?
Yes.
Let me know. Okay, here we are. Yes, this video summarizes what we've been saying. We have four different sites. The first of them is 5tonic, where we have a full 5G, and we are reusing the 5G core for connecting it to the RAN in Valencia. We have used 5tonic as well for testing, previous testing, before going to Ford, and then we have connected the RAN. Then we have the UPV site, where we have the servers for the edge platform. And we have Ford site, where the actual experimentations are done, and where we have the 5G coverage here. These are the images of the preparation of the devices. Use case 1. This is showing how the AGVs are coordinated. Then we have use case 2. This is the camera that recognizes the gestures from the operator. And depending on the gestures, that the operator is making, the AGV reacts. Here we can see how the AGV stops. And finally, we have use case 3 with the immersive monitoring with with some VR goggles. You can see where the AGV is moving, and you will get extra details of the environment in your VR goggles. And this is it for exfa Spain. So Dimitris.
Thank you very much, Diego. Okay, so next we're going to move to the presentation from Enrica Bosani from Beko Europe. Enrica, please, the floor is yours.
Thank you very much.
The exfa Italy, experimentation facility in Italy.
I share my screen. Is it okay? Do you see it? Do you see it? Is it okay?
Not yet.
Wait, let me
It
check.
says double click to enter full screen mode.
I am okay.
Unless it's on my side.
Okay.
No, the same comes for me.
Do you see now?
No.
No.
No. Why? I come back. I interrupt. I remove my camera. Maybe this will facilitate. Okay.
Yes, now it's working. Perfect.
Do you see now?
Yes, we can see now.
Full screen?
Full screen.
Okay, perfect. Thank you very much, and welcome everybody to the presentation of the Italia Experimentation Facility. My name is Enrica Bosani, and I am Manufacturing Innovation Project Manager in Beko Europe. Beko Europe is a pretty new company, born in April 24, so 3 months ago, from the joint venture between Whirlpool EMEA, the European division of Whirlpool Corporation, and Arçelik, which is a big Turkish producer and manufacturer and distributor of home appliances. We may count in Europe on more than 20,000 employees now in this moment as Beko Europe, and in 11 industrial sites in different countries in Europe. For the experimentation facility that we deployed within 5G-INDUCE, we leveraged on the premises in Cassinetta industrial site in the northern part of Italy, and in particular way in refrigeration factory. For this experiment with us, worked within the experimentation facility, the 2 technical partners, Wintra and KNIT, working on the infrastructure part, plus 4 partners working on the NetApp that have been developed and used to deploy the use cases that have been executed in our factory. Suite 5, Oculavis, iLink, and the Internet Institute. The testing area have been deployed in 2 different departments in the refrigeration factory of Cassinetta site. And in particular way, we used 2 areas, one within the warehouse department, and where we deployed the use case number 7 and number 8 that we'll see later. And the other 2 have been deployed in the primary process department, because we were mainly focused on maintenance, and we deployed there on 2 machines, one a thermoforming machine and a metal stamping machine. We deployed within this experimentation facility, we deployed mainly two different options in order to really fully test the potential of the 5G connectivity solution to support industrial environment. The first option is a deployment representing the public network solution for industrial environment. The 5G connectivity have been executed through the WINTRE public network that create the link between the devices, 5G devices installed in our shop floor, and the CNIT server where now and OSS have been deployed. In that case, this is a solution, no standalone solution, that had the possibility to count on a WINTRE 5G site in Comabio, that is a location near to the facility, the factory facility in Cassinetta, capable to cover both outdoor and indoor with 5G TDD and 5G DSS solutions. We used, in order to deploy the 4 use cases that have fully tested with this option, infrastructure option solution, we used SIM cards by WINTRE deployed with the public IP addresses that have been used both for the mobile devices used by operators and both used in the router and gateways and all the other devices that have been installed in the factory in order to deploy the connectivity. The second option, on the contrary, that have been deployed have been a solution representing really a private solution for the industrial environment. In this case, the connectivity between the shop floor and the CNIT servers, where now and OSS have been deployed, have been executed through a mobile test bed that you see here in the picture, that have been designed and built up in the CNIT laboratory. These represent a 5G microcell that have been installed in the shop floor and was used with dedicated private SIMs that have been used both for the mobile devices and for the gateways and routers that have been used for the use case deployment. In this case, we tested only the 2 use cases deployed in the warehouse department area because we installed this gateway, this mobile test bed in the middle of the center that have been dedicated to this area. There is a limited coverage of this solution, only maximum 10-15 meters. So we decided to select this area, which was much more interesting in this moment for our solution. The use cases that are 4, 2 of them dedicated to maintenance and deployed in the primary process area. One dedicated to safety, in particular safety control in the crossroad in order to grant the safety of the people and moving assets in the shop floor. And the last one dedicated to monitoring and control of the infrastructure. All of them you will see further detail later by the other partner that will describe in detail what we did in each of them. But summarizing the overall business requirements that we can address to all of them is mainly related to 2 main important elements that are the bandwidth and the end-to-end latency. That are the 2 most important elements with business impact that we had in mind to test in this solution in order to validate, demonstrate and validate the business impact of the introduction of 5G connectivity in the shop floor. For what concerns the setup, the infrastructure, in particular way here, I want to describe to you the area dedicated to use case number 7 and use case number 8 that have been deployed in the warehouse department. Here you see in the bottom right side of the slide, which is the outline, the outlook of this department. There are shelves, is a typical warehouse department that we have in the factory. Here in this area, we we identified and delimited the area with the anchors that you see here in red that are the sensors that were used for use case number 7, and we'll see later. And here in the gray bottom, that point that you see in the middle, you see where the mobile test bed have been deployed for the deployment of the option 2 solution for the connectivity. While in blue here you see the devices that have been used both in option 1 and in option 2 that are related both on the connectivity via public Wintry network and via mobile testbed with the private solution that have been deployed. Now I leave the stage to the colleagues in order to better describe the specific use case. In this case, Sotiris.
Thank you very much, Enrica. Hello, everyone. I hope you can hear me well. My name is Sotiris Kosouris, and I represent Suite 5, which is a software and AI solutions and services provider. And our work in this project, and specifically in use case 4, was to develop and test a network application that, as Enrica said, was focused on predictive maintenance for one of the thermoforming machines of the factory, in order to be able to provide to workers that work right next to the machine, but also to white-collar workers, insights and information about the processes that are going on and when maintenance should happen in order to prevent failures of this machine. So what we have been doing is that we had developed an analytics infrastructure that is actually capturing sensor data that are coming directly from the machine, and as well as images from a thermal camera that was inspecting the machine. And with the use of ERP data, we were in the position to execute predictive maintenance algorithms and feed back to the workers through a tablet, and also to the people that work on the offices through a web interface, important insights and metrics about the operation of the machine and the scheduled maintenance intervals. So if we go to the next slide, we'll see that we'll have the demo. So we will quickly go through a small video. This is the machine that will have been inspected. This is right in the factory. So we collected data from this machine, and using some dashboard, we were able to provide insights and data to the people that work on the machine, that have the opportunity to witness all those on a tablet right next to the machine, and actually be in a position to take decisions regarding the maintenance of the whole facility. So those analytics have been executed both over the now and on the edge. So in terms of benefits from this use case, following the evaluation we had, is that the presence of a 5G testbed and of the overall infrastructure allowed for the faster delivery of predictions, if compared to sending the data over to other providers that operate outside of the factory limits, like Google, DigitalOcean, and stuff like that. And that was actually because the whole round trip time and execution time was quite smaller. So we were in a position to timely identify and predict situations which could lead to defective products, so defective pieces of the refrigerator that might not have been picked up also during the quality control mechanism, and at the very end could be part of a fridge that goes out to the market and to the customer, which is something that we do not want to happen. And having in mind the pace that the machine is working, it is very critical to early and timely identify these defects. Otherwise, some pieces may go to the next stages of production and be considered as working okay, whether this will not be the case. So that was the main benefit, and this was conveyed to the right people at the right place, and with the right elements, like the right graphs, which were created with factory employees. We had user requirements to identify what they need to see, whether they're historical data or real-time data. And also one of the major benefit is that we were in a position, by utilizing the application and the 5G network that has been set up, to refrain from exposing data outside of the factory environment, let's say. So we're not sending data out of the premises of Beko, but everything has been executed within the 5G network, so no third party had access to this data. So as conclusions for this use case, which we have in the next slide, we can say that the 5G infrastructure has been tested and was in a position to deliver faster the predictions that have been delivered by the execution, by the analytics engine. We have performed tests with and without 5G-INDUCE, and the results were in favor of 5G-INDUCE. And this is something really crucial because at the very end of the day, we need to have in mind that the bandwidth that would be necessary for transferring and analyzing all this data is quite huge if we also consider images from the thermal camera. And if we are going to apply such a solution to similar machines that are working in the production line, then it's it's something that speaks out of itself. The bandwidth would be quite huge, and standard internet connectivity would not allow for faster transfer of this data to an analytics engine. With this in mind, we also have experimented with some other machines, and we found out that the analytics engine is in a position to also offer its services for other parts of predictive maintenance that are necessary within a factory. And this even strengthens the claim that we need fast networks, like 5G networks, quite, fast connectivity, but also the ability to have resources on site and manage them in order to be able to utilize similar applications to solve similar problems, which can be done with little investment, because at the very end of the day, it concerns the retraining of the models and the change in the data sources that we are using to feed this model. So that's it from use case 4 for the Beko site. So we probably will go to the next one. Thank you very much.
Thank you very much to you, Sotiris. Now the stage is to Jakob from Oculavis.
Yes, I hope you can hear me well.
Yeah.
Perfect. All right. Yeah, coming from predictive maintenance systems on the shop floor to actually solving issues based on these events. For example, you have just seen the image of a shop floor person using the use case 4, and now seeing that some you have some deviations and you need some maintenance. So actually have a planned maintenance, and also based on some machine failures to also have ad hoc troubleshooting and repair. And as factories can be quite big and also operating over internationally, where the knowledge is not on the same side, we are focusing here as Oculavis, as a software solution provider, on AR-based remote maintenance, repair, and upgrade. And here you see a couple of use case setups and industry stakeholders for this use case. So you see the machine supervisor in front of the machine, being able to use smart glasses or smartphones based on if he wants to or she wants to have it hands-free or not, or which devices right now available. You have maintenance operators who can be on the same site, which can be quite big, but can also be on a completely different country as where the process experts are. As I said, machine lifecycle here focus on plant maintenance and also on troubleshooting, and therefore I'm gonna show some videos on the next slide. What you see here is for the troubleshooting scenario, for example, wearing wearable smart glasses, where the machine has a breakdown, finding the right support here from the maintenance manager with video support. The important part is here, all of the industry shop floors are metal caves, which usually have not the best Wi-Fi connections, and especially also not the best connections. It's fine, you can leave it on this part, you don't have to play it again. And where standard solutions are not optimized for high quality transmission of video and audio. And we have encountered in the first test also that there with the standard solutions and let's say a standard environment where the latency is not that good and also the bandwidth is not sufficient to really achieve full HD or higher resolutions. And that's why in this scenario, we did deploy our media server via the interface in the 5G network, and did here the comparison of the tests. So yeah, which also is then very good in terms, of course, of latency, as the location was designed for this. If you go to the next slide, there's just another short video, which is maybe more driven by using, for example, for planned remote maintenance. The guy is still wearing the smart glasses, but also the same application is available there on the tablet. So to get the right remote support here with very complex equipment, so getting the right technical information on demand and also getting the remote support here using a tablet. Coming to the next slide, the business impact. Yeah, mainly we could achieve way more stable video remote collaboration, and also could increase the resolutions from, let's say, 720 pixels in video support, which were, let's say, okay, stable, to now really achieving 4K video support in terms of the bandwidth and latency, and also especially for stakeholders like the infrastructure, like the experimentation facility, and also from our side as an NetApp developer, the real benefit was the easy, let's say, interfaces and for our deployment. So in the end, from the XFAR, we could achieve a good user experience with a low latency and high bandwidth, which met the requirements that we were initially given. And in the end, this, of course, increases the worker efficiency, because not all the people have to travel for certain tasks there. You get the support from everywhere where you want. And also safety, because yeah, when operating with these machines, it can be quite critical, so that, yeah, low latency really is a high benefit that people can gain from. For us here also, we had a good test on the scalability. So for us, this means if we scale, for example, for the potential customer Beko to multiple locations, also that the system allows this to good scalability of the system based on the related number of connected users. And for this, also one more point to get this out is that with private network solutions of this 5G deployments, we also can meet industry standards, because yeah, data privacy with video on shop floors is a very critical topic. And with the knowledge of Beko, to have the media server not just in some, let's say, Microsoft Azure environment, to have it on their premises, which, yeah, bring here a better terms in terms of data security. That's it from use case 4, and I give over to use
Thank
case
you.
7.
Thank you very much, Jacob. Now the stage is to Panos Panagiotis from iLink.
Hi, Enrica. This is George. I will present instead
George.
because Panos is stuck in another meeting, so I will present. Hi,
Thank
hi
you.
all. I'm George from iLink, and this is a rather short presentation about use case 7, which is specifically focused on smart safety and industrial safety, to be more accurate. So the general idea is that we have utilized the ultra-wideband interlocation system to have a real-time location awareness of every moving entity within industrial facilities, usually large-scale industrial facilities, where the meaning of this use case is more robust and straightforward. So, as I said, we utilize the interlocation system, which is accompanied by all the software background and all the components that can access and analyze the data from the hardware, the anchors and tags. So if you could please move to the next slide, I think, yes, this slide actually showcases in the bottom right part the hardware components. As you see, initially we have conducted several tests in our premises and at the Beko factory. So at the latest tests, we have placed in specific places within the factory, the anchors, the most left image of the bottom part, and also the tags that are either placed on the clerks or are worn by the workers that are on foot. So here you see that, sorry, here you see that the system relies on the anchors and tags, a gateway that is responsible for collecting all the information and transmitting over 5G to the servers that host the Docker components for the location, for the calculation of the location. And also this system integrates a collision component that can project the movement of the entities based on their acceleration, their location, their speed, everything. So we can have a detection of an imminent crash. If there is a possibility of two different entities to crash, then we have an alert immediately raised, which also raises the importance of the 5G connectivity, the very low latency. And in this way, we have real-time monitoring and alerting, high scalability, because we can integrate a large amount of tags. And of course, there is a very significant and essential business impact to the elimination, actually the elimination of accidents, when applied to the full, to the entire facilities. So in the next slide, if you please may, yes, thank you. So the main output, here you can see the video, you can mute it, yes, thank you. So you can see the video when we actually tested at the Bekos facilities. You will see the tablets with the APK, with the application that provides the alerts. And on the top right, in the meanwhile, you can see the heat map produced, which actually depicts the places that most of the accidents have been observed. Here also the application has a green and red light. The red light indicates that the movement has to be stopped. Here is a blind spot, blind corner, where actually the blind corner makes this application much more valuable. And the top right image with the heat map actually can provide an added value about how the managers of the facilities can optimize the ergonomics and the placement of specific machinery and shelves in a way that will make the facilities much more viable and more easy to walk into. So as part of the decision-making benefits, as I told you about the maps, indicates the dangerous areas, the danger zones, and the mobile applications provide immediate notifications. We have also tested in two different, we try to test in two different options, utilizing the VPN and non-VPN connection. However, we used VPN and we managed to get very low latency within the limits, the KPIs we have set for the test. So everything worked properly. And I think with this slide, I have described the use case very briefly and with as much detail possible. Thank you.
Thank you. Thank you very much, Giorgio. Now the stage is for Inin, in this case, Yanis.
Yeah, Enrica, thank you very much. So good afternoon to all. Hello from Ljubljana, hello from Slovenia. So actually, with our use case, we are actually going back to 5G basics. So basically, our main target, or our, let's say, not just technical, but actually business driver to produce that kind of use cases, actually in the introduction of the 5G technologies, let's say, in these complex industrial environments. We believe if we want to have successful deployment of new technologies such as 5G, cloud native, and let's say future 6G technologies, we need to give to the end user a good visibility of the network performance, of the coverage assessment, and so on, of the solution or let's say of the services which are provided to them, let's say in our case to these industrial verticals. So our use case is about to provide the tool which is independent, let's say, from the technology provider. Who is providing the technology, we don't care, but we give the users, as you can see it here on the figure, a good visibility, let's say, to assess the performance of the services of the network which they are getting. This service could be provided by a private 5G network or could be provided, as we saw it in the case of Beko, over the public infrastructure. So our use case is about how to give more than 100 KPIs to end users, how to, let's say, visualize these KPIs, how to give them, let's say, a tool sets to use, let's say, in their, let's say, facilities such as handheld devices, industrial gateways, or in our case, we gave them also a drone, which means that they are able to fly over the facility with the drone and they are able to collect the 5G performance metrics from the radio, from the services perspective, and to assess, let's say, the coverage, to assess the performance overall on the area. So basically, we are giving this full end-to-end visibility from the perspective of QoS and QA monitoring. Of course, in live environment, we give them continuous monitoring, let's say, of SLA, SLS services in real-time, coverage assessment, troubleshooting, trending, and at the end, of course, when they're introducing new devices, also the performance prediction under, let's say, realistic load conditions. So please move on to the next slide. So because, of course, we are, let's say, providing advanced technologies, everything what we are actually building from the network application perspective should be cloud native. So in our case, let's say, the application which we are actually deploying in that kind of, let's say, industrial environment has more than 20, let's say, containerized components. It really depends, let's say, how complex the setup is. But you can imagine if you have a cloud instance, then you have 5G core network, you have a 5G edge, and then you have also RAN, let's say, environment. You can imagine how many components needs to be, or segments of the network needs to be monitoring and so on. That's why, you know, our network application is quite complex, as you can see it here. Actually, on the figure, we have really simplified, let's say, the view of our NetApp. But in essence, our target in the project was, let's say, how to, let's say, use the capabilities of INDUCE platform to fully automate the deployment of our, let's say, network application components. And as you can see it on this slide, we were able to do so, let's say, in less than 5 minutes in the environment, such a complex as it was in the Beko, where we were, let's say, having cloud components. We had, let's say, public 5G infrastructure, and then at the end, we had also, let's say, private infrastructure. So from this perspective, let's say the INDUCE platform give us really, really additional benefits. Why? Because let's say, if we are doing the deployment of our, let's say, application in classical fashion, we are using several hours or maybe even days, let's say, to deploy all the components in that kind of, let's say, environment. And of course, additional benefit which is coming out of the box from the platform is this automated system scaling and self-healing, which means if we need additional compute, if we need additional, let's say, storage capabilities, this could be done, let's say, fully automated independently through different thresholds and so on. So please move on to the next slide. So the conclusion, as you can see it here, and through the presentation, together, let's say, a simple KPI such as throughput, the application could be really, really complex. But from the end user perspective, it is really important that they have the visibility of the performance of the network. And if they have it, they will be confident to use the solution. And this is what we need, let's say, to push or to move on with the new technologies in that kind of environment. So automated of this testing and verification, we believe this is one thing which is really, really essential. Another point, what we want to give, let's say, to our customers and all the users of the 5G future technologies is that they will be actually able to predict the future. Predict the future from the perspective how the, let's say, networking services will behave under different, let's say, realistic, let's say, conditions and environment. So basically, from this perspective, of course, we need to give them, we need to collect high quality data. Of course, this is from historic perspective for the analysis. If we want to understand, of course, the current network status, this is something which is essential. But if we will combine historic and current, let's say, network status, KPIs and services KPI, this is how we will be able, let's say, to predict the future behavior, let's say, of the solution. So, but for the future, we believe that essential components, because we are collecting not just, let's say, some network and services KPI, but we are enriching these KPIs, let's say, with GIS information, with location information, with even with the video stream from drones, as you can see it here. That means that we are combining, let's say, different data, and to visualize this data and to give the meaningful let's say, output in real time to the end user, which are not experts for the 5G or cloud technologies. I believe this is something which in the future, of course, artificial intelligence and machine learning technique will be able to give us. So for sure, this is something which we are targeting in the future in our solution. And as you can see it here on these video clips, basically, we didn't limit ourselves just to deploy our NetApp, let's say, in Beko environment, industrial environment, but we actually collaborated with different 5G PPP sister projects, such as 5G Lugino, Vital 5G, where we actually deployed and used the components which were developed by 5G-INDUCE in, let's say, other, let's say, competing proposals. And that's how we are actually showcasing that we are not building the technologies which are silos, but they are fully open and transparent and so on. So that would be it quickly from our side. Thank you very much again for this opportunity. So at the end, for sure, I will be here open for receiving questions, if any. Thank you very much. Enrica, the floor is yours.
Thank you. Thank you very much. Thank you very much, Yanis. Let me check. That's all from what concerns the Italian experimentation facility. I hope that the picture was clear. A lot of things have been done, a lot of interesting experience. Now the stage is back to you, Dimitris.
Okay, that's great. Thank you very much, Enrica. And I think we should pass the floor now to the third experimentation facility, which is in Greece, and to Christina Lesi from OTE.
Good afternoon.
Hi, Christina.
So can you see my screen?
And we can see your screen, yes.
Okay, great. My name is Christina Lesi. I'm a network engineer in OTE. In this presentation, we will talk about the Greek experimentation facilities, and more specifically about the testbed that was used and the use cases that were demonstrated in this testbed. The Greek experimentation facilities are in Athens. Two industrial partners have cooperated to install the network infrastructure, OTE, which is a telecommunication provider, and PPC, which is an energy provider.
Christina, we don't see in full mode, and I think you are already in the third slide, but we see the first.
Yeah.
I think you have to switch the presentation.
I have. Can you see me changing slides?
No, I think you have to share the presentation.
Let me.
The full presentation rather than the initial.
Let me try again then.
Yeah, now it should work. That's a problem with Zoom.
What about now? Can you see
me
changing?
Yeah, now it's fine.
Okay, sorry about that. OTE, as the main telecommunication provider in Greece and member of Deutsche Telekom group of companies, is interested about using advanced telecommunication infrastructure to install new technologies towards the digital transformation of Greece. Additionally, through 5G-INDUCE use cases, which will be presented later on in this presentation, OT had the chance to identify the network requirements and design and implement a network that would support services offered to Industry 4. OT was also responsible for the installation of the network infrastructure, its configuration and performance. PPC is the main energy provider in Greece. PPC is planning through 5G-INDUCE use cases to earn new knowledge and insights on business activities improvement. It has also planned discussions with stakeholders on how the developed network applications can be incorporated in relevant field operations. PPC provided the facilities to install the network infrastructure and perform the use cases testing. The testbed had components installed in both OTE and PPC premises. The network infrastructure was based in 5G standalone Release 16 architecture, where 5G core was installed in OTE, and RAN, which was based in new radio technology, was installed in PPC. The distance between the two sites was about 15 kilometers. Additional components were used, such as OSS, an instance of which is installed in OT's cloud infrastructure, and Slice Manager. Slice Manager was a necessary component that allowed slicing. Slicing is the mechanism where a group of specific resources are available based on the needs of the use case. So for a use case that requires low latency but not that much throughput, the proper slice could offer only the available number of resources, allowing the better network resources management. The network coverage was extended in both indoor and outdoor areas. The area here in basement and the first floor over here was used for use case 6. The area in ground floor was used for use case 4 and the outdoor for use case 5. Here you can see the exact area that was covered for the 3 use cases. The RAN installation included 4 radio dots for indoor coverage and 1 outdoor antenna. There were also a BBU and an IRU installed in PPC premises. Antennas were 4x4 MIMO using 256 QAM and operating in 3.5 GHz. The 3 use cases that were tested in the Greek experimentation facilities were use case 4, predictive maintenance for power generator, use case 5, UAV inspection and surveillance, and use case 6, AR assistance for maintenance procedures. In this presentation, we focus on use cases 4 and 5. We will present the use cases description, showcasing, and conclusions. My colleagues, Sotiris Kousouris from Suite 5 and Ji Wang from University of the West of Scotland, will present use case 4 and use case 5 respectively. So let's start with use case 4. Sotiris, the floor is yours.
Thank you, Christina. Hi, everybody again. Use case 4 for the PPC case was more or less on utilizing the same network application that we have also developed for the Beko case, but now for a different problem. The idea was to actually monitor and deliver insights and predictive maintenance instructions for an electric power generator that is operating within the PPC premises. And what we have been doing with our application was to monitor real-time the condition of this power generator and of various important factors and metrics of the generator, and using this data and also some data from a thermal camera, trying to predict when maintenance should happen, as well as send back to the control room of the operator the necessary triggering instructions that could lead in automations regarding the operation of the generator. In the next slide, I think we have the video, if I'm not mistaken, Christina. No, we have the benefits, we have the video later. So let's go with the benefits, right? You will show later in a video how the setup was made and how the application was working. In terms of benefits, what we have achieved was to combine both edge and central processing of data that actually allowed to improve greatly the predictive maintenance operations and the accuracy of the predictions. So combining edge execution of analytics allowed us to improve the quality of the data and be in a position to transfer the data that was absolutely necessary for running in a central node some of the prediction algorithms. And we have used the now infrastructure in order to run the more resource-heavy operations that had to do with analytics. Through these applications, we show that it's really important, and this application could offer low latency for in terms of the monitoring and in the output of the machine learning results that could actually help safeguarding the operation of the whole generator. So imagine that a generator is running with different and high RPMs, revolutions per minute. So the circles it's operating. And this is really crucial when it comes to know when something is going to happen, which could lead to a failure or to a catastrophic event. And having that in mind, plus having in mind that this is a critical infrastructure, it was necessary and we achieved to be in a position to predict quite faster in terms of total time from prediction to triggering an event. We were in a position to predict quite much faster when something was about to happen and to trigger the necessary activities that are uptaken then by the workers and do the maintenance operations that are necessary, or even automate some of them by sending control signals to shut down smoothly, for example, the generator or lower its operation speed and so on. In general, the overall infrastructure allowed us to monitor both real time, but also have, based on historic elements, a view on what has happened in the past with this specific generator and try to predict what will happen in the near future. And this was actually really important for the operation of this facility. Finally, one of the side benefits, as in the case of Beko, was that the data was not necessary to be transferred outside of the PPC premises. And this is really critical as the infrastructure of PPC in total is considered critical infrastructure. It's power, it's an electricity company. So it's really important that assets are not exposed to third parties, even if those are claiming to be quite secure and so on. So if we go to the next slide, we'll see quite fast conclusions of the execution of use case 4 in the PPC premises. First of all, we have to mention that the overall 5G-INDUCE platform allowed us to rapidly deploy and control the operation of the whole complex system that consists of the analytics engine, the visualization engine, the data ingestion facilities, and all that stuff that need to be orchestrated in order to ingest the data, treat the data, and then extract the necessary intelligence and send it back, which is an operation that is really time-consuming and painful if it's been done over public clouds. So the overall now allowed us to do that quite faster than we do it in other cases. As I said before, the full time that has been recorded for the data transfer and execution of the analytics over the 5G network was lower than those of cloud-based resources that we use in other cases, which is really critical in order to be in a position to very fast take a decision of what to do next. And again, the 5G infrastructure allows us to place some components that in many cases are placed on a central cloud to take them to the edge, like data cleansing mechanisms, like data and quality control probing and data observability methods, which allowed to improve the overall, let's say, accuracy of our application. In the next slide, we have a video. So you will see that this is the electric power generator that was working in the PPC facility. And in the same room, there was a radio dot that was used to transfer the signals and the metrics to our application. Here we are in the central control room of the generator, where we also have 5G connectivity in order to utilize, the testbed that was available to transfer the data. And we see here in the rack where parts of the application have been installed. The application, similar to that one of Beko, had different views in the UI that allows to explore data of historical events, as we see here, for different types of events, of failure events, but also there was the possibility to have live predictions based on what the current operation of the machine was working. We cut it in granularity of 10, 15, and 20 minutes, if I'm not mistaken. And the operators could see different variables where, predictions could be made. So based on that, signals were being sent from our application back to the control room. And in a future scenario, this can be used for actually not only alerting operators, but also automating specific functions and actions that need to be done for safeguarding the operation of the generator. So that's all from my side for use case 4.
Thank you, Sotiris. Now we can move on to use case 5. See, the floor is yours.
Hi, thanks, Christina. Can you hear me?
Yes,
we can.
Okay. Hi. So hello, everyone. It's Chi from University of the West of Scotland, UWS. My pleasure to present use case number 5 on behalf of the team. Use case number 5 consists of 2 network applications. One is detection of corrosion on the surface of pipes available in mission-critical companies, such as the energy companies in the PPC case. The other network application is the detection of intruders, which is useful also for crime prevention, for public safety, etc., for the businesses. As you can see in the architecture of this use case, in the middle we have 2 components. One is the corrosion detection component. The other one is the intruder detection components. Both are based on AI technologies to help the detection. And then we have 2 other supporting components. One is the video proxy, which will receive the video from the drone through the 5G connectivity. And the other one is the message bus to enable the communications among the different components. And in the deployment, we have carried out in Greece. You can see using the OTE 5G testbed, we offer the 5G radio coverage for the UAV and the user equipment using a tablet to actually show the results of the detection of the corrosion on the pipes and also any intruders. And we have a core network managed by OTE as well. And then remotely, we have the CNIT to provide the 5G-INDUCE Orchestration platform through a VPN. Next slide, please. Yep. This slide summarizes some of the most important key performance indicators. So I'm going to highlight some of them. First, you will see the service deployment time, which is critical to showcase the performance of the platform to easily enable the onboarding rapidly for vertical use cases. So target is under 1 minute. We have actually achieved on average just above half a minute. And also for the connection part, to show how easily we can actually set up the network application using the platform to establish the connectivity and also configure all the parameters to make sure the network applications will up and running quickly. So again, the target is 1 minute, but we can achieve under 1 minute empirically. And then for the performance of the applications, you can see for the video quality is HD achieved. And for the end user perceived the latency, we have measured two. One is the time taken to start detecting the corrosion or the intruders. The other one is the video quality in terms of latency. So both are measured in the mean opinion scores. The maximum is 5. So on average, we achieved very close to 5. So almost perfect. And finally, you have the AI machine learning pipeline execution time. This is also important to measure the performance of the AI models. So we achieved close to real time, and in most cases, it's a real time in terms of both network applications for corrosion and intruder, in the range of 24 milliseconds per frame for the corrosion detection, and just about 40 milliseconds per frame for the intruder detection. Next slide, yeah. So for the conclusions, the 5G-INDUCE platform enables fast, scalable deployment of AI services, optimizing the resource allocation and reducing costs for vertical businesses. Especially this edge and core computing distribution has been enabled in a flexible way so that we can arrange the different resources across the different network segments. And thirdly, we have the network slicing also enabled in the platform, which guarantees the quality of service for the different applications, meeting the different requirements from the use cases. And finally, the platform effectively meet the diverse requirements from the different verticals. The benefits in 4 categories. So quickly, first, the rapid deployment and the scalability of the different use cases. Especially for our use case, we are concerned with the AI models and the quick deployment of the AI models, for example, in the edge platform, and also the scalability of the AI models. I'm going to show you a video demo at the end of the presentation. So you will see the performance of this platform and also the application. And secondly, the cost efficiency of resource management, especially for the GPUs, essential for running the AI models. So the platform has managed to achieve high cost efficiency in terms of these kind of computational resources. And thirdly, the flexibility in computing locations across the different network segments, the edge and the core, depending on the use case requirements. And finally, the quality of service are guaranteed through network slicing. Next slide, please. Now the video demo. So you can see we have done the experiments in the premises of PPC in Athens. Okay, I'm going to show you both the network applications, although we are focusing on the corrosion detection. Okay, so you can see first the drone operator piloting this UAV in the premises and connected to the 5G base station provided by OTE. And then this is the onboarding process of the different components to the 5G mobile edge computing platform connected to the orchestration platform provided by 5G-INDUCE. Now the video is streamed from the drone to the pilot and then to the 5G edge, where the AI model is running and then provide the analysis and the results returned to the screen of the operator. So you can see this highlighted corrosion already there. The next few slides showing you the GUI of the 5G-INDUCE platform to quickly onboard the different use cases. And in our cases, 2 network applications. And this is the actual setting in the premises of a PPC for the experiments. First, you will see the 5G base station on the wall of the building, and then the drone is flying to detect the corrosion of the pipes on the ground. You will see the team is closely monitoring the results on the screen of the tablet. So in this case, you can see highlighted here is a case of corrosion on the pipes, okay? And then also detection of the people acting as the intruders. And the team is now adding, more pipes with corrosion cases to test the effectiveness of the corrosion detection. You can see in real time, we can detect all the different cases of the corrosion. Okay? And together with any people acting as intruders. And finally, you can see the scalability of this AI-based solution. So we are flying the drone, and then you can see many simultaneous cases of corrosion are detected in real time. Okay, so this actually validated, the scalability of our solution and also the underlying platform of 5G-INDUCE. So this concludes my presentation. Thank you very much.
Thank you, Chi. So with use case 5, we have completed this presentation. Thank you very much.
Thank you to all. We are almost close, to the 2-hour slot that we have allocated. From my perspective, before actually closing, I would like, first of all, to thank everybody for this very interesting project, because it was a project that it brought different stakeholders together. So it was from the development of the platform that was presented earlier, to different network applications, all the use cases from all the partners that you have seen. And these use cases were actually demonstrated on actual facilities, which is very important actually for the developers, for the participants there, in order to promote essentially the different applications, because all the participants, of course, have a more commercial view of the products. The good thing was also that there was a lot of feedback, so there were many cases that were actually directed from the companies, from the factories, about, for example, what are the needs. Some examples are the corrosion, which is very difficult to be detected, or, for example, the safety in back of factory, with people working in. Maintenance was also part of for both Suite 5 and Oculavis with specific solutions. And it was also very unique cases, as you see in the experimentation facility of Spain, about how to coordinate different solutions to coordinate HEVs, quite innovative solutions. So that was a blend of different actors that were successfully put together. All of this information now will be available. I'm not sharing my screen, I should be. So as you see here, this information, including today's video from the workshop, will be available through our website very soon, and it will be also information will be sent in LinkedIn. We have a YouTube channel where you can see all of the videos, and even more actually showing today, and quite lengthy, with more details. And please keep also the final link here. We are keen to exploit this further. If you have questions, but even if you have remarks, or if anybody would like to establish some further collaborations with the different stakeholders, what we have seen, we're keen to actually answer to this, or direct you to the appropriate people. Before closing, very quickly, I think we have 1-2 minutes. If there's any final remarks or questions from the audience, we'd be happy to hear right now. Okay. So I said it's always we are open, okay, for your remarks, either through LinkedIn or direct email that they will send to us. Many thanks to all the presenters. Many thanks also for the audience in this presentation. And I hope that you found it interesting. Okay, thank you very much.